Cool. Welcome, everyone. It's my pleasure to introduce Rankeya Datta, from University of Illinois, Chicago, who will tell us how valuation rings behave like regular rings. Rankeya.
All right, thank you for the introduction. And I thank Eloisa and Sean for inviting me to speak in this seminar. And it's nice to see you all in the pandemic. So today I'll talk about how valuation rings behave like regular rings. And this is going to be based on joint works with Karen Smith and Benjamin Antieau. And so the point I want you all to take away from today's talk is that the class of rings that I'm about to introduce are very, very not Noetherian. But despite being non-Noetherian, they're going to have striking similarities with regular rings. All right. So throughout the talk, K is going to be a field. And let me just define what a valuation ring is. So valuation ring V of K is going to be a subring of K such that for all X and K, either X is in the ring or its inverse is in the ring. And so I'm going to discuss some properties of valuation rings now. And then after discussing the properties, I'll give some examples. So first of all, a valuation ring is a local ring. And when I'm talk about local rings in this talk, I don't necessarily mean Noetherian. So it's a local ring with maximal ideal given by the set of elements in K whose inverse is not in the ring V. It's going to be a normal ring, so it's integrally closed in its fraction field. And then it has this striking divisibility property that gives rise to all good properties of valuation rings in this talk. So for all X and Y in my ring V, either X is going to divide Y or Y is going to divide X. And this just follows from the fact that if you assume without loss of generality that X and Y are both non-zero, then either XY inverse is in the ring V or its inverse, YX inverse is in the ring V. And those two relations implies either X divides Y or Y divides X. So that's roughly the reasoning. And as a consequence of this divisibility property, the strong divisibility property, you have the following very nice result, which is that finitely generated ideals of a valuation ring are actually principal. And how do you see this? Well, if you have a finitely generated ideal, you're going to take a finite set of generators x1 through xn of the ideal. But based on property 3, you can assume without loss of generality that the first of these generators divides all the other ones. And then the ideal is just going to be generated by this first generator that divides all the other generators. So that's an easy proof. And again, as a consequence of the divisibility property, you also have the fact that the set of ideals of V are going to be totally ordered under inclusion, which means that given any two ideals I and J, either I is contained in J or J is contained in I. So if you restrict your attention to the set of prime ideals or the prime spectrum of the ring, this implies that the spectrum of a valuation ring is just a chain of primes. All right, are there any questions about the properties and the definition? Okay. So let me give you the first, so the talk is about how valuation rings behave like regular rings. So let me give you the first indication of how valuation rings behave like regular rings. So here's a lemma. So valuation ring V of a field K is going to be Noetherian if the value, if a valuation ring V of a field K is Noetherian, then this implies that either V is the field K itself, or V is regular of dimension 1. So let's prove this. So without loss of generality, assume that V is not the whole field, so it's a proper subring of K. So what did we just see in the list of properties? We saw that finitely generated ideals of V are principal. So this tells me that every ideal of V is principal because V is Noetherian, so all its ideals are finitely generated. All right, so what's another name for a ring, a Noetherian ring where every ideal is, a Noetherian domain where every ideal is principal? Such a ring is a PID. Thank you, yes, it is, thanks. It is a PID. And what do we know? We know that a PID, in fact, in this case, it's a local PID. So a local PID is regular of dimension 1. A global PID is also regular, but in particular, the local PID is regular of dimension 1. And another name for a local PID is a discrete valuation ring. All right, so this is the first indication that valuation rings behave like Noetherian rings. They're Noetherian if they're the field, a field, or a discrete valuation ring. So the upshot is that valuation rings are usually highly non-Noetherian. Okay, so let's do some examples. So I've defined the class of valuation rings, we've discussed the properties, and we've already seen a way in which they behave like the regular rings. So here's the first example, and hopefully one that we've all seen at some point in our lives. So if A is Noetherian in normal, suppose A is a Noetherian in normal domain, then it's R1 and S2. R1 means regular in codimension 1. So this means that for all prime ideals, P in A, such that the height of P is 1, the localization of A at P is a valuation ring. In fact, it's a discrete valuation ring. It's a Noetherian valuation ring of Krull dimension 1. And these Noetherian valuation rings give rise to the theory of divisors in algebraic geometry. So that's one of the most common ways in which valuation rings prop up in algebraic geometry, and even in commutative algebra. So let's do another example that you may have seen from arithmetic. So the ring of p-adic integers that I'm going to denote by ZP is an example of a valuation ring. It's in fact going to be a Noetherian valuation ring of Krull dimension 1. So both my first two examples are Noetherian. So let's give you an example of a non-Noetherian valuation ring, and let's see using this construction how naturally these valuation rings arise. So what I'm going to take next is I'm going to take the fraction field QP of the p-adic integer ZP. And now I'm going to do a construction that may be familiar to some of you. I'm going to take the integral closure of the p-adic integers in an algebraic closure of the fraction field. So this is also known as the absolute integral closure of the p-adic integers. So this is going to be, and I'm not claiming this is straightforward to see necessarily, but this is going to be an example of a non-Noetherian valuation ring of curl dimension 1. And if you take this absolute integral closure and then take its completion with respect to the ideal P, so then this is also going to be a valuation ring. And if you're interested in mixed characteristic stuff, this very simple looking ring is an example of what's called an integral perfectoid algebra. And these integral perfectoid algebras, if you're interested in these kinds of ideas, or at least the p-adic completion of the absolute integral closure of the p-adic integers is a fundamental object in p-adic Hodge theory. So valuation rings are currently in vogue because of their applications in p-adic Hodge theory and rigid analytic geometry. All right, so given some examples, are there any questions before I state the main theorem of today's talk?
When you take the prime ideal in that ZP closure,
Yes.
that's an idempotent prime, right?
Yes. Well,
Okay.
yes. Yes. Okay. So the main theorem today is going to be the following theorem proved with Benjamin Antieau, and it's that valuation rings are derived splinters. And I'll tell you what I mean by this over the course of the talk. Now, first, even before defining what a derived splinter or a splinter is, I'm going to compare this result the following result, the direct summand theorem due to Hofstadter and Andre. And what does the direct summand theorem tell us? It tells us that regular rings are splinters. And I'll again define these objects in 1 second. And then we have the following generalization or strengthening of the direct summand theorem called the derived direct summand theorem due to Berkovich. It says that regular rings are derived splinters. So this is further evidence of how valuation rings behave like regular rings, which is one of the goals of this talk. Okay, so what's a splinter? Let me first introduce what a splinter is, then I'll talk about a derived splinter. So we say a ring R is a splinter, and I'm not assuming anything is Noetherian here because valuation rings are not Noetherian. So ring R is a splinter if any finite ring map phi from R to S that's surjective on spec. That just means that the ring map satisfies the lying over theorem, is pure. And what does this pure mean? Pure is also known as universally injective. Pure means that if you take any R module M and you tensor the map phi by the R module M, then the resulting map is injective. So this is the right definition to make in a non-Noetherian context. You might have seen this definition as be saying that R is a splinter if any finite map that is surjective on spec is split, but splitting is not a good notion in a non-Noetherian context for finite maps even. So, but an example is that split maps are pure. So if you don't like to think about the notion of purity, you can just think about splitting. So phi splits, by which I mean if phi has a left inverse in the category of R module, then it's pure. Because if phi has a left inverse, then when you tensor it by any module, the resulting tensor product also has a left inverse, which means that the resulting tensor product is also injective. Okay. So as a first lemma that will be very useful for the proof of the splinter and derived splinter property, I'm going to prove the following result. So let V be a valuation ring, then any finitely generated torsion-free V module is going to be free. That's the result I'm going to show. So let's assume that I have a finitely generated and torsion-free module M, and I'm going to assume M is not 0, because then there is nothing to prove. So what am I going to do next? I'm going to choose, it's a finitely generated module over a ring. So what I can do is I can choose a minimal generating set. The proof is very much like the proof of Nakayama's lemma. So I'm going to choose a minimal generating set M1 through Mn, where because M is not 0, the module M is not 0, and it's going to be bigger than or equal to 1. And once I have a minimal generating set of this torsion-free module, my claim is that this minimal generating set is in fact free. Okay, so how do we see this? So suppose it's not free. So if a generating set is not free, this means that there is some non-trivial relation among the generators. So this means that there exists x1 through xn in V, not all 0, such that I have a non-trivial relation among the generators. All right, but we're working in a valuation ring. So then what can we say about these xi's? Because we're working in a valuation ring, there is a divisibility relation among any two of these xi's. So then, without loss of generality, what I can assume is that x1 divides xi for all I. But now I'm going to be able to deduce the contradiction. All right, so if x1 divides all the other xi's, what I can do is I can divide the equation by x1 and express m1 in terms of the other generators. So this tells me that m1 is going to be negative x2 over x1 m2 minus so on, negative xn over x1 mn. But then this is not possible because I chose a minimal generating set. So the small n here has the smallest possible cardinality, and I just expressed one of these generators in terms of the other n minus one of them. So this contradicts the minimality. So assuming that there is a non-trivial relation, I deduced a contradiction, which means that there is no non-trivial relation. It just means that the M1 through Mn is in fact a free generating set of the module M. Okay, any questions about this lemma? So what did we show? We showed that if you have a finitely generated torsion-free module over a valuation ring, then this is free. So if you remember your first course in graduate algebra, then you can compare this result I just showed with the following. So this is one of the first results you learn when you learned about the structure theory of modules over a PID. A finitely generated torsion-free module over a PID is always free. So here is another way in which valuation rings behave like regular rings, because a PID is a regular ring. Okay. Questions so far? So if a finitely generated torsion-free module over a valuation ring is free, then this leads to the following nice characterization for torsion-free modules that are not necessarily finitely generated. So the corollary is that a torsion-free module over a valuation ring is always flat. So what's the proof? The proof is fairly straightforward. So what I'm going to do is I'm going to express the said torsion-free module as a filtered union of its finitely generated submodules. But any submodule of a torsion-free module is torsion-free. And if I have a finitely generated submodule, then it's free. So it's flat. And a filtered union of flat modules is flat. So these finitely generated submodules are free and it's flat. And then I just use the fact that a filtered union of flat modules is flat. Okay. So as a nice consequence of this corollary, I'm going to leave the following exercise for you to do if you're not interested in the rest of the talk. It's going to be a 1-minute exercise, really. So if V is a valuation ring, and if M is a finitely presented V module, then as a consequence, you can show that the projective dimension of M as the V module is going to be less than or equal to 1. So this exercise should remind you of the other property of regular rings, namely that finitely generated module over a regular local ring has finite projective dimension. So this is the analog of that fact for valuation rings. Finitely generated is not really a strong enough notion to guarantee finite projective dimension, but the analog of finitely generated in the non-noetherian world is finitely presented. And this shows that for finitely presented modules, there is in fact a constant bound on the projective dimension on such modules, independent of the module. All right. So are there any questions so far?
Yeah, can you generalize like some of these previous ones about the finitely generated torsion-free being free and so forth? Can you generalize that to like a proofer domain where you've only got finitely mini-maximal ideals?
So if you have a proofer domain, right? For example, flatness can be checked locally. So any torsion-free module over a proofer domain is also going to be flat, because proofer domain, the local rings are all valuation rings. So that should work. I am not sure about the finite generation bit. So I think a finitely presented module over a proofer domain is going to be locally free.
Thank you.
You're welcome. Okay. So now, as a very easy consequence of the results I've proved so far, we can give a simple proof of the following analog of the direct summand theorem. So valuation rings are splinters. And this proof is going to be much easier than the proof of the direct summand theorem. So again, splinter means that if you have a finite map that's surjective on spec, then this map is pure. And in fact, in this case, we'll show that if you have a finite map from a valuation ring that's surjective on spec, then the map actually splits. So it's stronger than just being pure. So let V be a valuation ring. And now suppose that I have a finite map, phi, from V to S is finite and surjective on spec. All right, so if it's surjective on spec and V is a domain, what I can do is I can choose a prime ideal of S that lies over the zero ideal. So choose a prime ideal P in spec S such that this prime ideal lies over the zero ideal of V, which is prime because V is a domain. So now what I'm going to do is I'm going to take the following composition. So the composition given by, I have the map from V to S, and then I take the quotient map from S to S mod P. Because P contracts to 0, this composition is finite. It's finite because I've composed two finite maps. And it's injective. because P contracts to 0. All right, so what I have now is a finite injection of domains. So this is a domain and this is a domain. So if I have a finite injection of domains, then the target domain is always torsion free. So I have a finitely generated torsion-free module. S mod P is finitely generated and torsion-free, which means that S mod free is free as a V module. So therefore, S mod P is free. So it's a direct sum of a finite number of copies of V, and I can split off one of these copies. So this shows us that this composition splits. If this total composition splits, if this has a left inverse, then this map is also going to have a left inverse. It's just going to be the composition of the surjection with the left inverse that we had before. Which completes the proof that valuation rings are splinters. Much easier than the direct sum theorem that took 4 decades to prove, or 5 decades. I'm not quite sure. I think Mel proposed the result in the early 70s. So that should mean about 4 or 5 decades. Okay, questions? All right, so I'm going to proceed toward the main result, which is to show that valuation rings are derived splinters. But before I do that, I'm going to embark on a brief digression. So suppose I have a ring A of characteristic P. So then recall that in characteristic P, you have this following fantastic theorem of Kuhn's, which is that if A is noetherian, then A is regular if and only if the Frobenius map on A, which is the pth power map, is flat. So here is the analog of Kuhn's theorem for valuation rings, which was the result I observed with Karen Smith. So for a valuation ring V of characteristic P, the Frobenius map on V is flat. So in characteristic P, valuation rings behave strongly like regular rings in this other aspect. So here's the proof. Again, proof is not hard. So I look at this Frobenius map, and then I look at the target copy of V. I consider this target copy of V as a module over the base using restriction of scalars. And then the target copy of V is torsion free because this is a map, injective map of domains. So the target copy of V is torsion free as a module over the domain via restriction of scalars. And so it's flat because when you have an injection of domains, and the Frobenius map is going to be an injection because V is a domain, the target is always torsion free over the base. And that's precisely what it means for the Frobenius map to be flat. And so as a consequence of the valuative Kuhn's theorem, you can deduce that the Frobenius on a valuation ring is always pure. Or in other words, V is F pure, if you know what that means. And then this observation with Smith was the starting point of a joint work where we developed a theory of F singularities for valuation rings that I'm not going to talk about today. Okay. Questions before I transition from CARP to derived splinters? All right, so let me introduce the notion of a derived splinter now. So for a ring A, I'm going to first define the derived category of A modules. Well, I'm not really going to define the derived category because I don't have enough time. So dA is going to denote the derived category of complexes of A modules. So the objects of this category are just complexes of A modules, but the morphisms in this category are more complicated. And this is because of the fact that any honest map of chain complexes that induces an isomorphism on cohomology is actually invertible in the derived category. So all I'm going to say today, and I apologize for this, is that the morphisms in this category are complicated. But we don't really need to know much about the structure of the derived category for the rest of today's talk. Okay. So suppose I have a morphism of scheme. So X is a scheme over spec A, and I have a morphism F from X to A, spec A. So what I can do is, or I guess first, I'm going to define this object called R gamma of OX. So I can take an injective resolution of the structure sheet, just like you take injective resolutions of modules. You can take this global injective resolution of the structure sheaf. And then the object R gamma of XOX is going to be a complex. So I'm going to take the injective resolution, and I'm just going to apply the global sections functor to this injective resolution. So this is going to be the complex obtained by applying the global sections to the injective resolution. And so each of these modules is a module over the global sections of OX, which itself is a module over A by restriction of scalars. So this is going to be a complex of A modules. So it's going to be some object that lives in the derived category dA. And observe that if you look at the zeroth cohomology of this complex, so this is the kernel of this map from the global sections of I0 to the global sections of I1. And because taking global sections is left exact, this kernel is precisely going to be the ring of global sections of the structure sheaf. So as a sanity check, if the map F is finite, then this R gamma complex that I just introduced is in fact going to collapse to just the global sections. So what do we have so far? We have that the kernel is the zero, the kernel, or rather the zeroth cohomology is just the global section. So what do we get? We then get something called an F that I'm calling F sharp in this top. It's going to be the map from A to its global sections. That just comes from the morphism of schemes F. And then this global sections is going to have a map because it's a kernel of a complex that resides only in non-negative degrees. There's going to be a map from gamma, the global sections, to this R gamma complex. And now, with all of this terminology, we can define a derived splinter. We are going to say that the ring A is a derived splinter if for all proper, surjective, and finitely presented morphisms, and finitely presented here means that locally on X, the affine open neighborhoods look like a polynomial ring modulo of finitely many polynomial equations instead of infinitely many polynomial equations. This is something you have to take care of because A is not Noetherian. So finitely generated need not imply finitely presented as algebras. So A is a derived splinter if for all proper surjective finitely presented morphisms F, the map F sharp, which goes from A to R gamma, has a left inverse. In the derived category. It might not have a left inverse in the ordinary category of complexes, but we want it to have an inverse in the derived category. So that's the definition of a derived splinter. And again, here, finitely presented means finitely presented as algebras. Okay, so let's do some examples. So suppose you are a finite type algebra over the complex numbers. Then Kovacs showed that A is, I'm going to call derived splinters as just D splinters. So A is a D splinter if and only if A has rational singularities. And Berkovich showed the following very surprising result in characteristic P. So if you assume that A is Noetherian and has characteristic P bigger than 0, then A is a D splinter if and only if A is a splinter. So the derived version of a splinter is the same as the underived version. This is a very non-trivial result. And I believe Berkovich has recently proved an analog of this result in mixed characteristic as well. Okay. Any questions so far? So in the remaining, I think, 13 minutes, I'm going to try to give you a sense of the proof of why a valuation ring is a derived splinter. Okay, so what do we want? We want that a valuation ring V is a derived splinter. And what we're going to do today is we're not going to prove this in full generality. We're going to do a very special case. So we're going to sketch the proof when the valuation ring V is absolutely integrally closed. Which I'm going to abbreviate AIC in the rest of the talk. And absolute integrally closed just means that the fraction field of V is algebraically closed. So the proof that I'm going to sketch today is not much more general than the proof for any valuation ring. Okay, so what's the idea? The idea is that if V is absolutely integrally closed, then what you can do is you can approximate V by regular rings. And once you can approximate V by irregular rings, and I'll tell you what I mean by this precisely in 1 second, then you can reduce to Batz's derived direct sum and theorem. Okay, so first order of business, I want to tell you what I mean by approximating V by regular rings. So this is going to be a consequence of de Jong's theorem on alterations, and I'm not going to tell you what the theorem of alterations is, but de Jong's theorem on alterations, it's going to be, de Jong's theorem of alterations is a form of resolution of singularities up to finite extensions of the ground field, but this alterations theorem has the following nice algebraic consequence for us. It tells us that if V is an absolutely integrally closed valuation ring, over, say, its prime ring, which is either Q in characteristic 0, FP in characteristic P, or the integers and mixed characteristic, then this V can be expressed as a filtered colimit of finite type regular K subalgebras. So you should think of this result as a weak analog of the still open problem of local uniformization of valuations. The absolute integral closure or absolutely integrally closed valuation rings admit a weak form of local uniformization in the sense that they are a colimit of regular rings, or in other words, they are in smooth. Okay, so how does this help us? How does expressing this valuation ring as a colimit of regular rings help us? It says the following. So what I'm going to do is I'm going to write my V as a colimit of AI, where these AIs are honest regular rings. And now I'm going to pick a map F, which is proper, surjective, and finitely presented, because those are the types of maps that appear in the definition of a derived splinter. And here it's important that my map F is finitely presented. So once I express the base as a colimit of the spec or as an inverse limit of the spec of these AIs, then there are some very nice but non-trivial approximation theorems that tell us that I can choose an index I and some Fi over spec AI, which is going to be proper, surjective. I don't need finitely presented anymore because AI is noetherian. So finite type is finite presentation over noetherian rings. And such that this X is obtained by base change along the map from AI to V. Or in other words, this is saying that we have a Cartesian square, a fiber square, if you will, where again, this X is just the base change. I'm not claiming that this result is easy, but it follows from the fact that I have a finitely presented morphism and that I have approximated V using these regular AIs. Okay, so what does this tell us now? So on the left-hand side, this vertical map is something nice in the noetherian world. It's proper, surjective, and it lives over a regular ring. So now I can use derived direct summand to conclude that the map from AI to R gamma of xi oxi splits in the derived category of AI modules. So now the obvious thing to do then is to use the splitting at the level of AI and pull it back to V. So this then tells us that if we pull back, we get a splitting of the following map of complexes. So this map is going to split in dV. And because AI is a flat AI module, this left derived tensor product is just going to be V. It's just the usual tensor product. So I have a map from V to this left-derived tensor product that splits. So we would win. Okay, so we'd be done if this tensor product complex here was our gamma of XOX. So again, let's go back to the diagram here. We are taking the structure sheaf at this level. This R gamma is like the derived push forward or of the structure sheaf. That's this R gamma of X, Xi OXi. Then I'm taking the left derived tensor product and pulling it back. But I can do this the other way around. I can first pull back and then push forward. And when I pull back and push forward, the object I get is going to be this other complex. So what we're saying is, because this square is a Freiberg product square, one would hope that pushing forward and pulling back is going to be the same as pulling back and pushing forward. But alas, life is not fair, so this doesn't happen. So life's unfair. So, but the technical term for experts is that this fiber product square may not be something called Tor independent. I'm not really going to define Tor independence today. But then how do we fix this? How do we ensure that we do indeed end up with an isomorphism like this? Or how do we make the square Tor independent? So one way to ensure Tor independence is if this vertical map Fi is flat. Then I'll have whatever Tor independence is. And Tor independence for us just means that this isomorphism of complexes holds. So one way to ensure the isomorphism is to make the Fi flat. And this Fi was obtained by approximating F along the co-limit. So what I can do is, if I can make F flat, then again, by some non-trivial approximation result, I can choose I such that Fi is flat in addition to being proper and surjective. And then I'd be done. Because if Fi is flat, then I'd have this isomorphism. And once I have this isomorphism, I get a splitting. So how do I make this first map F flat? Is the point of the rest of the talk. I guess I'm almost out of time. So let me just quickly say this. So I'm going to choose J to be the torsion ideal, the V torsion ideal of X. And then I'm going to look at the closed subscheme of X given by the vanishing of this torsion ideal. And then, because taking the closed subscheme is killing torsion, the map from Vj to the spectrum of the valuation ring is flat because I've killed torsion, and torsion-free modules over a valuation ring is flat. This is flat, I've killed torsion. This is also proper because closed immersions are proper and I've composed two proper maps. It's surjective, this is not hard to check. But now what I've done is I've killed an ideal in a non-noetherian scheme, and I don't know if this ideal is finitely presented. So there is no way for me to tell a priori that this Vj is finitely presented as well, which is something I need for these approximation theorems to work. But it turns out that this is finitely presented. And this is by the following very surprising result of Renaud-Grousson. And the result is that if I have a finite type and flat map from a domain A to any ring B, and A is a domain that is not necessarily Noetherian, then the map is automatically a finite presentation. So of course, if you live in the Noetherian world, this is a very trivial result. But we're working over non-Noetherian rings, which makes this result highly non-trivial. So what's the upshot? The upshot is that this composition here is now a proper map that's finitely presented, flat and surjective. So, and this is the last part, the composition splits. And because the composition splits, so if this composition splits, the first map is going to split as well. So hence, so does the first map. And the composition splits by our reduction in the previous, on the previous page. And that's the end of the proof. And I'll end my talk here. Sorry for going over time.
That's just fine. Let's thank Rankeya for his talk. And are there any questions? Feel free to unmute yourself to ask your questions or put them in the chat.
Okay, so I have a question. So from a very naive perspective, the moment you said, you know, when you have an absolutely integrally closed DVR, you can approximate it by regular rings, I thought, oh, well, no wonder they look like regular rings, right? So I'm wondering if in the general setting, if you just have a valuation ring, is there any sense in which you can approximate it by regular rings?
So that's one of the open problems in valuation theory, says that if you have a valuation ring, then it has a center on an irregular ring. That's the local uniformization problem. So at least for function fields, let me be careful. If you have a valuation ring in a function field of a variety, then it dominates some regular local ring. And this is known in characteristic 0. It's the problem of local uniformization. And it's wide open in characteristic P in dimensions bigger than or equal to 4. So it's a local analog of resolution of singularities. And in fact, Zariski used these local uniformizations to prove global uniformization for small dimensions in characteristic 0. So that's a great question.
So then I take it that...
Sorry?
Oh, my question was, you said something about the dimension being less than or equal to 4. So are you assuming something about that these valuation domains are finite dimensional?
Well, no, the point is that local uniformization is known in dimensions 3 or less. Well, where the dimension of the variety is 3 or less. Okay. I'm not assuming, so when I say dimension, sorry, I should be more specific. When I say dimension, I mean the dimension of the variety, okay, not the dimension of the valuation ring. Yes, that's a fair point.
Other question.
Sorry, go ahead.
Nope, you.
So one thing one should be careful about is that I just told you that the absolute integral closure of a valuation ring, or rather an absolutely integrally closed valuation ring, can be approximated by regular rings, but the absolute integral closure of a regular ring cannot be approximated by regular rings. So this is something very specific to valuation rings. And there are obstructions that come from local cohomology, like Singh's examples of local cohomology modules with finite infinitely many associated primes give you obstructions. Yeah.
So this is what I was going to ask, though, is, right, so the valuation results in the Noetherian setting are essentially proving that you know, DVRs are derived splinters.
Yes.
So what, I mean, is there a a two-dimensional or higher dimensional analog? I mean, if you take the absolute integral closure of a two-dimensional regular local ring,
Yes.
can you prove that that's a derived splinter?
Wait,
And
sorry,
before
my
you
theorem
answer
was
that
about
question,
any
what does
valuation
DVR
ring.
mean?
Sorry, a two-dimensional regular local ring.
So what does DVR mean?
It means it's a regular ring of regular local ring of dimension 1, the maximal idealist principle.
Okay, because DVR oftentimes for valuation domains means that the value group is some finite number of copies of Z. But I mean, it depends
Yeah.
on what notation. So DVR in this case means noetherian, correct?
Noetherian, yes.
Okay.
So Sean, going back to your question, my result was about arbitrary valuation rings, not just DVRs. The DVR case is already true by direct summand, right?
I agree.
Varga's result.
I agree. So I'm making an analog. So that my real question is, or was, if I take the absolute integral closure of a two-dimensional regular local ring,
Yes.
can you prove that that's a derived splinter?
Oh, that's a good question. I do not know.
Because that would be the version in this context of higher dimensional regular local rings being splinters.
Yes, I would be surprised if that was a derived splinter, but just because.
Or even a regular splinter.
Yeah. So absolutely integrally closed rings are regular splinters because there are no finite extensions in a way.
Okay, fair point. So then derived splinter.
Derived splinters, I'd be surprised if that's true, but I do not know.
Thank you.
So
you're welcome.
So I have a follow-up to my previous question from the discussion. Then I gather that you showed us a proof to the special case, but your proof in the general case should be completely different then, because you don't have this approximation.
So what
idea.
happens is, what I do in the general case is I take a valuation ring V, all right? Then I'm going to take its absolute integral closure. That's going to be not a valuation ring necessarily, but it is something called a proofer domain. And I can take one of its local rings, which is also going to be absolutely integrally closed. And it's going to be a faithfully flat map. And then I'm going to use some finiteness and cohomology results to say that derived splinters descend along faithfully flat maps. But those are non-trivial. So yeah. You're welcome.
Other questions? All right, let's thank the speaker again.
Thank you.